section 5.3 is called Modeling Data Using Polynomial Functions, and what we're going to be doing in this section is more regression. You might remember we did regression in a previous chapter with logarithmic and exponential functions. We're going to do pretty well exactly the same thing, but this time we're going to use polynomial functions, which we've just learned about. So, quick reminder about what regression is. It's a process used in statistics, which is a branch of mathematics, to estimate the relationship between two variables. So for example, in this first question here, we're going to be looking at time and concentration, and we want to know what's the relationship between time in this question and concentration in this question. And the way we did this with logarithmic and exponential, we did this two ways, one with the graphing calculator and one with Desmos. And what we found at the time was Desmos was a heck of a lot easier and a lot faster, and for that reason, or those reasons, I'm only going to use Desmos in this lesson. If you're interested in using the graphing calculator, you can go back and look at the previous lesson. I believe it's called Modeling Data Using Logarithmic and Exponential Functions or something like that, and it's exactly the same process for what we're doing today, but I'm going to use Desmos. So there's only two questions we're going to do today. The first question is the concentration in milligrams per liter of a medication in a patient's blood is measured as time passes. Susan has collected the following data and is attempting to express the concentration as a polynomial function of time. So here we have time in hours after medication has been given to a patient. This is the amount of medication in the blood, and what Susan's looking at here is there's some way of expressing this data with a formula. Basically, that'd be very useful. So what we're going to do is we're going to create a scatter plot of this, and then we're going to do regression, and Desmos makes this very easy. So the first thing we do is we go to desmos.com, and we're going to enter in a table. So we hit table here. And in the X column, I'm going to put the time values. And the time values, I'm not going to flip back and forth, but if you look at your sheet, the time values are 0 and 1.5 and 3, 4.5, 6, 7.5, and 9. And then in the Y column, I'm going to put the concentration, so that starts at 0. At time 0, I guess there's no medicine. Then it goes 26.9. 41.2, 47.8, 46.0, 36.8, and 20.3. And there we go. And all I see is 1 point here. Why is that? Because the window is too small. We need to make the window bigger. So I hit graph. And what I'd like is I'd my X to go up as high as, well, above 9. Let's put it up to 15. That might even be too much, but what the heck. And then for my Y, I want it to go up above 50. How about 55? And there you go. I can now see them all. And what the question again it wants us to do is to create a scatter plot, which we've done, and use a quadratic regression feature to determine the polynomial function. So if you look at this, doesn't this not look like a quadratic? This looks like a parabola, doesn't it? An upside down parabola. So that tells us it's probably quadratic. So what we're going to do is we're going to write it in the regression. So we put y1, and we don't put equals, we put this symbol right here, the regression symbol, and what we're going to do is write this in general form. So we're going to put ax squared plus bx plus c. So ax1, and we need to square that, ax1 squared plus bx1 plus c. That's the general form of a quadratic equation. And as you can see, we get this parabola showing up, and it's doing a really nice job going through most of those points. I think we have what we need here. So the first question is, create a scatter plot, determine the polynomial function c equals, now you can't put t's into Desmos, we put x's instead of t's, but that's fine. That best fits the data, we've done that. Round the parameters a, b, and c to 2 decimal places. So basically we're going to write this formula down, and we're going to do some rounding. So what we have here is c equals, now we need the a value. So we go back here and we look at the a value. It's negative 1.86 if we round to 2 decimal points. So c equals negative 1.86x, but in this case we're using t, and it's actually squared, plus, but before I put plus, let's see what b is. Yeah, it's positive, so plus 18.76 plus 18.76, and t, right, instead of x, t, and then I need my c value, so I look at c, and it's 1.21. So plus 1.21. And there we go. There is the function that relates those two variables, time and concentration, in this question. Very useful. So if you wanted to right now, you could figure some stuff out by putting numbers in for t or numbers in for c, and we'll get there in a second. First of all, it says there's domain restrictions on the quadratic function determined from the data. Explain and identify these restrictions. So domain, remember, is x, or in this case t, it's the input value, and it's time. So if we're looking at time with this individual, what do you think the smallest amount we should be looking at? I would say it's 0, right? You don't really want to go below 0. That'd be before they're getting the medication. It's not really of interest. So I would say the domain goes from 0 up until how much? Well, this is all of interest to us. This is where the medication is going up and up and up and up, and it's going down, 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 down. And then what happens right here? This is when there no longer is any medication in the system. This is kind of nonsensical here. Now you have a negative amount of medication. No. So this is the limit right here. At this point, we're no longer interested. So the domain at this point is 10.16. So we're interested from 0 to 10.16. So that's the restriction. So you could put 0 is less than or equal to x, which is less than or equal to 10.16, or you could put square bracket 0, 10.16, square bracket. And the reason it's from those two numbers, here's where you first are given the medicine, and here's where the medicine's now gone entirely from your system. The doctors decided that the patient needs a second dose of medication when the concentration in the blood is less than 10 milligrams per liter. If the first dose of medication was given at 9 a.m., at what time should the second dose be given? Okay, so we want to know, when is it less than 10 milligrams per liter. Milligrams per liter is the C value, or the Y value if you look on here. So what we want to know is, when does the Y amount, when does it drop below 10? So remember how we do this? We actually plug in here y equals 10, and we'll get a horizontal line. There it is. Now there's two places it intersects. Here's one of them. Is this of interest to us? Not so much, because the medication is still increasing here. So this is fine. What the doctor's concerned about is when it drops below, which is right here. So at this point right here, this is when the doctor figures you need another dose. And when does that happen? It happens after 9.6 hours. So your answer is 9.6 hours later. But what we want to know is what time that is. Well, 9 hours after 9 o'clock is, well, it takes 3 hours to get to noon, another 6 hours, so you have 6 p.m. But what about this 0.6? How do we deal with that? What we can do is find out what's 0.6 of 60, because that's how many minutes there are in an hour. So 60 times 0.6 will give you that answer, and if you do that, you'll find it is 36 minutes. So at 6:36 p.m. it's time to give another dose of medicine according to the doctor. Okay, all the questions are like this, but the only thing that differs is whether it's a quadratic, linear, or a cubic function. So let's take a look at this one. A research student was investigating the relationship between job satisfaction as measured by employee on a scale from 1 to 10. So they ask you, hey, how satisfied are you with your job? And this person's really satisfied. They're 10 out of 10. This person's not satisfied at all, practically. They're 2 to 10. And productivity, P, as measured by the employer on a scale of 1 to 100. So the employer's asked, hey, with this guy right here, what would you say his productivity is? Only 44, not very good. How about this guy here? 98, really productive. And we have data from 12 employees here. And what we're looking at is if we can get a relationship between these. We're looking for a regression. So the first thing we have to do is graph all this data. Let's do that now. So I'll get rid of these. I'm going to chain, well, why don't I just get rid of it and start a new table. And here we go. Again, I'm just going to enter it in pretty quickly here. So in the X column, we've got the first person 3, then 8, 7, 5, 9, 6, 6, 10, 8, 2, 5, 7. And in the Y column, it is 44, 81, 75, 60, 66, 90, 70, 71, 98, 75, 25, 68, and 77. Okay, and again, when you do that, you can't really see much of anything. We need to change the window. So with the x's, the most I see is 10. Let's go a little bit above 10. Actually, 15 is fine. We'll just leave that. With the y's, let's go, we need to go up to 100 to be able to see everything here. And there you go. So what does that look like, first of all? Does it look quadratic? No way, it's not quadratic. There's no parabola there. Does it look linear? Yeah, it absolutely could be linear, couldn't it? And that's the first part of this question. It says the student looked at the scatter plot and suggested that the productivity could be expressed as a linear function of job satisfaction. And that kind of makes sense too, right? If you're more satisfied with your job, you're probably being more productive. I mean, look at number 10 here. Number 10's really satisfied with their job. They're maximally satisfied, and wow, look at their productivity. If you look at number 2, who's not satisfied at all, they're very low productivity too. So it seems sensible that it's a linear function. So we're going to do a linear regression and determine the relationship. So a linear, remember, is like mx plus b, or in this case aj plus b. So let's do that now. So we're going to put y1 not equals, but the regression is regressed against mx1 plus b. And there you go, not bad at all. It goes close to a lot of the points, right through a few of them. And so we can write down our equation. Our m value is 7.91 and our b value is 19.89. So let's write that down. Y equals 7.91 x plus 19.89. Of course, I've done this wrong. It's supposed to be p, isn't it? And it's supposed to be j there. So we'll change that. It's supposed to be p equals 7.91 j plus 19.89, where p is productivity and j is job satisfaction. Good. However, another student looked at the scatter plot and suggested that the relationship could be represented by a cubic function with a point of inflection. Remember what that means? That's the cubic one where it's like this, and this is a cubic, the point of inflection right there. And if you look at that data, that does look somewhat possible that there's a point of inflection there. So what we're going to do is we're going to do a cubic regression and see if it's any better. So let's try that. I tell you what, I'll turn this one off and I'll do a new one down here. So we have y1 regression is regressed against ax cubed. You have to do this in general form again. So ax1 cubed, so I have to hit cubed, plus b x1 squared plus c x1 plus d. And hey, if you look at that, that's pretty good. That looks pretty accurate. Like that might be better. Let's compare that one and that one. Which one looks better to you? I think that the black one is better. I think the cubic is closer to the actual thing. So we're going to have to write all this down. Our a value is 0.32, our b value is negative 6.37, our c value is 45.90, and our d value is negative 44.21. I'm going to put all that into this equation right here. So I'm not going to flip back and forth. I'm going to look at my sheet here. So I have p equals a, and the a value was 0.32 j cubed, plus b, and the b value is actually negative, so that's wrong. Got to get rid of that. I mean, you could put plus negative, but I prefer just put minus, and it's 6.37 j squared. The c value is positive. It's 45.90 j, and the d value is negative. It's negative 44.21. Wow, that is a long cubic function there. And what we said, or what I said, is I think this blue one is actually better than the red one. It's more accurate. So which model do you think represents the data better? I would say the cubic, which is this one right there. Okay, there you go. Once again, you gotta love Desmos for making our lives so easy here. And it's free.